So we have, of course, all these phenomena. We know nature works, but what are the theoretical ideas underpinning this? And the theme of unification is a wonderful one, because we have seen actually that there's the incredible power of ideas to unify many, many different physical phenomena. And actually, the Institute for Advanced Study where I work has kind of a motto which is truth and beauty. And that actually is a very interesting philosophical theme. And great scientists have spoken about this. For instance, there's a wonderful quote by Hermann Weyl that if he had to choose, he would often choose beauty, just the power of ideas. Or Paul Dirac, who was even more adamant that it's more important for equations to be beautiful than to fit experiments. Although if your theory doesn't really quite work in practice, it certainly looks less beautiful, I would say. But then there's another perspective. I like the remark of John Wheeler, a great physicist, black holes, nuclear physics, worked on that any law, when pushed to the extreme, is kind of approximate and statistical. Or Francis Crick from Watson and Crick fame, a theory that explains all the facts is wrong because usually some of the facts are wrong. So that kind of tension between beautiful ideas and the conflict with reality is something we'll see many times. And of course, I want to start with a little parable, which is a story from the old Greeks. So the old Greeks had their own theory of everything based on mathematics. In fact, for them, mathematics, the most beautiful thing were these 5 geometrical objects, the Platonic solids, the most perfect objects in math. And they had a theory of everything which was loosely based on the equation 4 + 1 = 5, because the 4 elements out of which they thought everything was made of corresponded to these 5 objects. You see kind of the square was kind of nice. You can build out matter out of it, so that would be the element Earth. The tetrahedron was kind of pointed, so it would hurt, so that would be fire. And then there was the 5th element, which was the dodecahedron, and actually they felt that stood for all the matter outside the Earth. That was Plato's conjecture. So the planets, the stars, the heavens would be made out of a different kind of material. And in fact, if you go even in art history, you often see this beautiful figure of the dodecahedron, and it's kind of symbolizing, I would say, kind of metaphysics, the things that actually we are hearing about today so much. Now, in fact, it's even here in the old meeting room of the Dutch Parliament, and I was just the other day reading some description of it in a newspaper, said, well, is it quite appropriate to have a soccer ball hanging in this hallowed grounds? But, so we went from the structure of the universe to soccer. But I'm telling the story because I want to tell a story about Kepler. Kepler, a famous, of course, astronomer, and he was really in love with this kind of mathematics, and he had his own theory of the universe. When he was a young man, this basically explaining the universe, what at that time meant just the orbits of the 6 planets. And his equation was essentially 5 + 1 = 6. Because he took the 5 Platonic solids and fitted them in kind of a model. You can do that in many different permutations. And he found one that up to like 5% accuracy gave the ratio of the size of the orbits of the planets. Now, it's a silly theory for many reasons. There are more planets, there are more solar systems, etc., etc. But the great thing is that he himself destroyed his own theory by careful observations. And Kepler, of course, is famous by observing that the planets do not move in circles, but in ellipses. And an ellipse is kind of an ugly circle. It's one that's squeezed on. And certainly it can have all kinds of different shapes. And Kepler himself writes in his diary when he discovered this, I'm taking a horse cart full of manure into science. Because certainly his theory is very ugly. Now we think, no, it's absolutely beautiful because all these orbits are in fact explained in terms of mathematical figures. They're conical sections, and in fact there's a beautiful theory behind that. That's the classical mechanical, the orbits of classical mechanics that Brian explained, which go back to Newton. And so there's beautiful mathematics there. And in fact, the French astronomer Lagrange once said about Newton, no, he must be the luckiest man ever to live in the history of the planet because there's only one system of the world and he's the one who discovered it. So, very powerful statement. Now, of course, Newton didn't add that, and we should emphasize is that he really unified concepts because he unified the physics, the everyday physics, literally the falling apple with the movement of the planet. So in some sense, taking away the need of any kind of quintessence of fifth element describing the universe outside the planet Earth. Now, there are many, and I'm just skipping through that, just give you one example of a historical measurement which was the same kind of unification. It would be the 19th century equivalent of finding another particle. This is the discovery of infrared. I like the painting because it's painting something you can't see. It's actually Herschel measuring the temperature of light, first in the blue, then in the red, and it puts the temperature outside the spectrum, the rainbow, and he measures that it's even hotter there. So it's a wonderful moment because certainly you see something that wasn't there before. And of course now we know that this rainbow, the colors of visible light, they stretch around this huge spectrum of electromagnetic waves. And so that's a terrific example of unification because all these things are just the same phenomena. In fact, electromagnetism, Brian explained some of it, is a great example of unification. These are the portraits of Maxwell and Faraday, and show them because actually I just recently saw these two small portraits that we still have. They actually are coming from Einstein's office. So if you wonder who were his heroes, actually it was Faraday and Maxwell that were hanging there, and he was looking at them every day, and I hope being inspired by that. Talking about Einstein, I think, and this here I want to add some of the things that Brian talked about, which will be crucial for our further understanding. I want to kind of think of his contributions also as kind of a unification, namely unification of space and time. So let's go through this. And because that will be extremely crucial to understand the modern theories of particle physics. So one way to think about it is, so we want to understand this concept that time is an extra dimension, the fourth dimension. And I'm actually explaining this with a very simple example. So behind me, you see a movie. So these are just kind of two particles orbiting. And think of all the different stills, the pictures out of which this movie is made, and cut them apart and put them on a stack. So if you put them on a stack, you will see actually here on the left, we get the various pictures one by one, and we're moving up in the vertical dimension, which is time. And so clearly, you know, this is the earlier pictures are on the bottom, the later pictures are on the top. And Einstein basically said, well, think of this not as space plus time, but think of this in this case as a three-dimensional material. Glue them together. So they can be one big solid object, which you see here on the right-hand side. And you see that what were the particles, the red and the green particle, they now became this kind of spaghetti strands going up. We call them world lines. And while we are sitting here, actually, each of us is forming this world line, going through space and time. Physicists actually look at the right-hand side as physical reality. It's space and time. You see basically the whole movie at once. You see the whole history of the particles at once. And it's diagrams like that that we want to draw and actually help us explain how modern theories are. Now, bringing you to the modern age, which is the age of particle physics, it's actually quite a challenge. So if you look at the pictures coming out of these accelerators, just this very thought that there is simple structure, there's a theoretical idea, there's mathematics underpinning this is pretty challenging. It looks like kind of garbage to the naked eye. And in fact, there were many times in the history of particle physics where people thought that perhaps it is. That nature is kind of a black box. You can see what comes in and what goes out, but you couldn't open it like modern electronics or something. And in fact, in the 1960s, this was one of the lines of thinking, kind of a holistic way of thinking that, you know, we're never to know. And we shouldn't even ask the question. Well, I would say in retrospect, that couldn't be kind of the worst point of view, because the box can be opened. And I like to say, you know, inside the box is this little formula. So here I use the power of mathematical symbols to write down the formula, which essentially is the formula for the standard model. And that formula, you could give a lecture to mathematicians and they would understand each of these symbols. They might not understand the implication for physics, but all the symbols there, I would say, are beautiful, are elegant, and kind of make sense. Now, this is not really the formula that you get taught if you do a course in high-energy physics. I took a course in the Netherlands. Actually, I called that, the textbook we used the formula on the left-hand side. That's by Tini Veldman, the Nobel laureate. And he really wanted to emphasize, that there are many terms and it's hard work. Of course, it's hard work. But as you also see, basically the standard model can be put on a T-shirt. And that's an amazing achievement. You see these, of course now with Higgs added to it. 17 particles basically describing all of nature. That's a terrific achievement. And so one thing I want to get across, how? What are the ideas underpinning that theory? And to do so, and you should realize, by the way, that this is a book that you can get. That's the Book of Particle Physics. This would be the list of particles that people would have presented, for instance, in the 1960s, with all their properties. But in some sense, we want to describe. We not only want to describe the world around us, we also want to describe everything produced in these particle accelerators. And the fact that that simple formula explains that thick book, which is really like a telephone book of particle physics, is an amazing achievement. I want to move to the heart of the matter. What are particles? What are fields? What is the modern way to think about particle physics? And I go back to a very elementary question, a question that perhaps you didn't even realize physics can answer. Now, if you read about electrons or protons or other particles, you read about the property of the electron. So how do you know that every electron has the same properties? Is there a factory in the universe that makes electrons and do it with absolute precision? How come they're all exactly the same? Now, there's a great story about how we think about this, and it actually goes back again to John Wheeler. In fact, John Wheeler and his graduate student at that time at Princeton, Richard Feynman. And Feynman describes this story in his Nobel Prize lecture. So in the middle of the Saturday evening, he's called by Wheeler and says, I know why all the electrons are the same, because there's only one electron in the universe. And let me explain his theory. It's really a crazy theory. So here's again our space-time picture. Time is running up. Here's an electron. And suppose this electron, it should go up in time, like we all are going in time. Second by second, we're going up. Suppose this electron is allowed to go back in time. Suppose I'm allowed to go back in time. I can kind of go outside, come back, and stand next to myself. And I would have exactly the same properties. I would be basically cloning myself. So that would be one way. So Wheeler suggested, suppose that the electron can go up and down and make this kind of big knot. And now think about this as a sequence of pictures. So in the bottom picture where you have one electron, but if you basically cut this whole thing in the middle, you will have a lot of particles basically coming up and going down. Electrons and positrons, particles and antiparticles. And they would of course all be the same because it's the same particle. It's a pretty amazing description of particle physics. Well, allegedly, Feynman immediately said, well, if that's true, there should be as many electrons as positrons, etc. And so that theory didn't go much further. But actually, these diagrams we have seen already today. We now call them Feynman diagrams. In fact, I'm very charmed by this page out of Feynman's notebooks, because this is actually the first page on which he's kind of trying out this idea. He's literally sending the particles back into time and discovering that you can send them back and that the mathematics actually works. You can do this. Particles can go up and down, and he's drawing these diagrams, which are particles with exchanging other particles, and then he's fantasizing that at some point all the physics books, which at that point were filled with calculations and big algebraic expressions, would all be diagrams. And actually that's true. If you look nowadays in particle physics books, you'll see Feynman diagrams everywhere. And so this was an absolutely terrific way to understand particle physics. And there's a kind of a nice story that at some point there was a graduate student walking in, I think in LA, and he saw this van driving. And he said, wait a moment, there's Feynman diagrams on the van. And he stops the van, and it's a lady driving it, and he said, madam, I really have to stop you, because do you know that actually these pictures on your van, they are called Feynman diagrams, and this is like very interesting in physics. And then she says, yes, I know, I'm Mrs. Feynman. And here's the van, physical proof of the van. In fact, these diagrams are even crazier than you think. So one thing that actually can happen, and that's what quantum mechanics allows. I mean, quantum mechanics works on this principle that anything basically goes as if you do it fast enough before it's detected. And so, for instance, a particle could go up, it could split in two particles that then join together and go on. The particles in the middle might violate various laws of physics, and so they are not detectable. They would be what we call virtual particles. They exist, if you wish, on paper, in our thoughts, in our calculations. They're not the particles that you are made of or the particles of light that we see all around us. In fact, you can even have this crazy thing, which is a pair of particles appearing out of nowhere, and then a particle and antiparticle, and then annihilating again. Or perhaps this is something that Wheeler really would have liked. Think it of as a single particle going up in time and back in time and endlessly looping around. Now, this is not something that's just happening on computer screens and in our minds. This is actually happening right in this room. So if this is my own kind of attempt of an animation of what it would look like if we could see these particles. So even empty space, the space around us, is filled with these processes of virtual particles appearing and disappearing again. It's the rules of quantum mechanics allow this. In fact, they determine that this must happen, and there are lots of physical effects related to this. In fact, the Dutch physicist Casimir was the first one to discover this. We call this Casimir energy, Casimir effect. You see it in many, many different areas in physics. So the empty space, through the laws of quantum mechanics, is actually filled with a lot of dynamics and these kind of processes that are allowed and that kind of to a classical mind wouldn't make any sense. And in some sense, the ultimate consequence of this, and we have heard about this, and I will say a few words more later, is that these processes would fill all of space-time. And actually would make space-time not only an interesting material, as Einstein argued, but actually gives it physical properties. It would fill it with energy. Now we call it dark energy, but it would be an energy computable in principle if we understand these processes. Now these processes are treacherous because literally everything that's out there in the universe will happen in this particular form. So it's very difficult to compute this if you don't have a fundamental knowledge of all processes that are happening. Now, another element underpinning, apart from the nature of space and time, particles going up and down, is the concept of symmetry. So we're basically back to the old Greeks, as symmetry as the unifying principle underlying all of modern physics. And one way to think about it is actually a very simple way. It's going back to quantum mechanics. Brian showed that in quantum mechanics, a particle is described by a wave function. Technically, this is a complex function, and it would have a phase. You can kind of basically rotate the wave around in complex space. You can add a complex number to it of unit length, and this would not be visible. So there's a kind of a symmetry that's invisible. You would rotate the wave function, you wouldn't see this. And you can do this essentially at any point in space-time. So even in the description of quantum mechanics, there's a huge symmetry that we call actually a gauge symmetry. It's you rotate a piece of the wave function here, you rotate there in another way. And actually to do this, you need kind of a compensating field. You need a, what mathematicians would call a connection, but what in physics is called a vector potential. In fact, it's the vector potential underlying electromagnetism. So the modern point of view of electromagnetism, of light interacting with matter, all comes down to this particular symmetry. It's a symmetry of nature, and by implementing the symmetry of nature, you get a field, the electromagnetic field. The electromagnetic field then, under the laws of quantum mechanics, where waves and particles can be interchanged, will get the character of a particle. Basically, by taking a wave and kind of minimizing the amount of energy in the wave, you at some point, that's the original idea of quantum mechanics, you get little quanta, little bits of energy, goes to the very beginning of quantum mechanics, of Planck in 1900 and Einstein in 1905. And so you can actually argue that this mathematical object becomes a physical field, becomes a particle. In fact, it will be a massless particle of spin 1. That's determined just by the theoretical structures. And a modern way to look at the electromagnetic forces. So think about we have two magnets or two charged objects. They have a force that they're interchanged. It's a 1/r² force, just as in gravity. The modern way is that it will be transmitted by particles. So there's a force-carrying boson, the gauge boson, that produces that force. Now, one point here, because you might say, wait a moment, if I put two magnets, I don't see light flashes going from the left to the right. Where are these photons? Can you stop them, for instance, by put your hand in between it? These are virtual particles. So these are particles that describe these processes. They're not particles. The wavy line in between, as it stands, is not something you can actually measure in general. And so it's part of our description, but it's a crucial way to describe that particular force. And in fact, this way of understanding electromagnetism is key to understand all the forces that are relevant for particle physics. And take for another example the strong force, that the strong force acts on the nuclear constituencies, on the quarks. Quarks come in, so to say, in three colors. So they're very similar to the wave function of an electron. However, it doesn't have a phase, it has kind of an arrow. So you should really think about it. It's actually a good metaphor, because any color you see is a constituent of the three elementary colors, red, green, and blue. So actually, a color is a vector in three-dimensional space. And so a quark has this kind of vector in three-dimensional space that can rotate around in any possible direction. If you actually think about symmetry, so here I've tried to visualize how you think about it. So if you have a quark field, that field would be ever in space and could be rotated around. This would be a global symmetry, where every point in space-time, the symmetry acts in the same way. But the symmetries in nature are much, much larger. In fact, you're allowed to rotate that in every special point. So the first was more like a communist model, all in sync. This is more kind of a chaotic model, where every particle is allowed to rotate in any way he or she wants. And so this huge symmetry is out there. And in a kind of a bit of a metaphorical way, you can think of the force fields as kind of collective waves in all of these kind of objects that are rotating around, kind of the color field as it is at each different point in space and time. So symmetry is absolutely crucial, but then you should take these symmetrical objects and bring them in the realm of quantum mechanics. And if you do it in quantum mechanics, you get pictures like this. For instance, this is a process very similar to a process where two electrons would interchange a photon and get the electric force. These are two quarks interchanging a so-called gluon, which is the equivalent of a photon for the strong force. You see a red quark can turn into a green quark and vice versa by interchanging an intermediate object, which would be a red-green object. A gluon that is now labeled by two charges, two colors. In fact, this logic tells you that you don't have a single gluon, but you would have a 3x3 matrix of these objects interchanging the force. And there's a small mathematical subtlety that in the reality it's not 9, but it's 8. It's kind of the diagonal element of the matrix gets removed. But this is actually how nature works. These kind of colored force particles are the ones that actually, by which the quarks interchange their nuclear forces. And in fact, there's a great thing here, because if you would do the equivalent of shining two light beams to each other, but now made out of these gluons instead of photons, you see actually that the gluons themselves can interact. For instance, a red-blue and a blue-green gluon can fuse together and make a red-green third gluon. So these forces are complicated. They can't travel over long distances. They kind of tangle up through their self-interactions. But their self-interactions are given by a very clean mathematical rule. For those of you who know, this is a matrix multiplication. So it actually is the theory of matrices, of linear algebra, the theory directly of group theory that actually is used to describe the interactions of the force-carrying particles. So this all kind of makes wonderful sense. And in some sense, the only thing that you have to know about the standard model, if you're a theorist, is, okay, I know there's a symmetry group underpinning the whole thing. Give me the symmetry group. And this is the answer. After a painstaking series of experiments, decades of struggle, we came to this final line, the little formula sitting in the black box that I opened. And so it tells you what the symmetry of the standard model, so of the particles that we know is. It's U1 cross SU2 cross SU3, and it's a kind of a telegraphic shorthand of what the content of the standard model is. And it's describing for you both the electroweak force, which are the usual electromagnetism and the weak interactions of radioactive decay, for example, and the strong force that holds the nuclei together. So that's one thing you have to know. You have to know, give me the symmetry group. And the second thing you have to know, give me the matter and how it's represented, how the symmetry group acts on the matter constituencies. In the same way that we said quarks can have 3 colors. So what are kind of the colors of all the particles? And this we have seen in Maria's talk, so that's actually just giving you the matter content of the standard model. And in a mathematical way, that's just a representation of the gauge group. So you need 2 things from that point of view, a gauge group and a representation. And then kind of the mathematics take care of it. It tells you how the forces are interacting with matter, how the forces interact among themselves. I think this is a fundamental way. We should realize that this is something that really has played over the last 100 years. It's a fundamental way in which we describe nature in terms of matter on one hand, forces and radiation on the other hand, and a very specific logic how the two are interconnected. Are there any questions about this point of view? And in fact, I should say that the physicist Lorentz was essentially the first one who sketched this way of thinking about nature. Of course, in those days, it was just light interacting with matter, light interacting with electrons. But in some sense, we have generalized that understanding to all of matter and all of the forces. Yes?
Is there anything special about this particular symmetry group?
No.
Is there any way to understand why this and not other symmetries?
That's the perfect introduction to my next chapter, because there's one sense, well, wonderful, you just give me this group and we're all set. But then why this group? Why not SU7 and is this the most beautiful, most special symmetry group that's there? No, there are candidates for exotic things called E8 or something, which perhaps mathematicians would say, well, if you have to pick anything, pick this one, because it's totally unique and special. This looks like kind of run-of-the-mill. So why? Now, this is in some sense a summary, a little bit more detailed, of the particles in the standard model with some of their properties, their masses. For instance, you see on the right-hand side these masses. So there are always these kind of 2 feelings you have if you're confronted with this. First, what a terrific power of ideas. Simple mathematical structure and a handful of particles explaining everything we see around us here, really every physical effect. And then the second question is, okay, so tell me more about it. Tell me more about the parameters, about the properties, why this particular group. And then you get this famous question that once was asked about when the muon was discovered, who ordered this? Why these particular particles? Why these masses? Why these properties? Why does every matter come in kind of a family? And why do we have 3 of these families, roughly small, medium, large? Why the groups, indeed, SU3, SU2, U1, they might have some special properties, but are they totally unique? Is there some kind of intrinsic way why nature picked this? So it's almost like we understand some of the physical laws. We know the law, but then the question is, what is the specific solution to the law? Newton's laws of gravity are universal. Our solar system is just a specific example of that. How unique is this model? And there are many questions about this. And so people speculate. For instance, if you look at the particles and antiparticles, and you use the fact that we just learned about, that neutrinos have a small mass, which was kind of totally unexpected and doesn't fit within the standard rules of physics, within the standard model, you have to presuppose, if you can presuppose, another neutrino, a very heavy neutrino that I put here on the right-hand side here. It's a particle that we haven't discovered. It might be there. If it's there, it's probably very, very massive. But then the theorist's mind takes over, and people look at this diagram and say, well, look at these particles within a single family. Can we rearrange them in a nice way? And for instance, they can be rearranged in this way. This is a kind of a 5-dimensional hypercube. And this suggests that there is a bigger symmetry, that there is a symmetry what we call the grand unified symmetry, a symmetry group that would contain as a subgroup the U1 cross SU2 cross SU3, but for instance here is SO10. Now, whenever you do this, whenever you unify, now that is a familiar pattern. You unify, so you simplify, but at the same time you produce also more effects, and you're also predicting more effects. Time after time we have seen this. So any of these attempts to unify the standard model will actually give suggestions of other particles. And so you have to find a good explanation why you haven't discovered the particles. They might kind of mess up some of the wonderful properties that the standard model has, that namely that it's quantum mechanically consistent, there are no so-called anomalies. It's kind of really a very fine-tuned Swiss watch. So if you start to mess with it, you have to be careful not to destroy that. But this is a line of thinking about bigger symmetry groups that are in some sense are broken in the same way as some of the symmetry groups of the standard model are broken. Well, we already heard a lot about dark matter. Clearly, this is something which is outside the standard model. So any theory that predicts new particles is certainly, we need something like that because there's a huge part of the universe. We aren't made out of it, but it's out there that has to be explained. And we also learned about the dark energy being there and how much actually is not yet explained. So I think theoretical physicists have these two frames of mind. They really want to understand in more details the theories we know. But we also know that in some sense this is preliminary. And perhaps any progress is preliminary, but we are in a very interesting point because we're on the threshold of understanding the 95% of the universe that's still out there and unknown and not described by our theories. And in the same sense, our theory is also crying out to be extended. And perhaps this is the two things can go together, and we really can push beyond what's known at this moment. And I think it's also important to realize that that's one of the aims of a theoretical physicist. You like to predict or to map out that part of nature that's not yet mapped out, and by the strength of our idea. So one thing I want to emphasize with you is that there is this great phenomena that here are depicted the four fundamental forces of nature, the three forces acting on the elementary particles, electromagnetism, weak and strong, and then there's the gravitational force. And this animation shows how these forces change their character if you move to higher and higher energies. And I actually want to explain how this happens and why this is important. But the great thing of physics is that it's not as invariant as you might think it is. And I want to go back to a very elementary question. It's another of one of these why questions. So think about electromagnetism and think about the strength of electromagnetism. So take two electrons and measure their force between them. Well, it goes as like 1 over r squared. There's a good reason for that. In modern parlance, you would say that's because we have a massless particle, a photon, interacting the force. But then what is the size? What is the size of the strength? And there's a coefficient there that you can compute. It's proportional to the square of the charge of the electron. And it's called the fine structure coefficient, and the mathematical symbol for it is alpha. And so the question is, how strong is the electric force? And you can compute alpha if you know what the charge of the electron is, and you find it's roughly 1 over 137. Now, for a long time, people actually thought it was exactly 1 over 137. And you can find many papers in the past that people were really fascinated by the number 137. Why 137? There's a famous story of Pauli, Wolfgang Pauli, famous physicist, at some point at the end of his life, was in this hospital room, which is number 137. So he was really spooked by that. In fact, there's a great story, perhaps you know, about Sir Arthur Eddington, the one who actually verified the solar eclipse and the bending of the light and made Einstein famous. He had, in the later phase of his life, a theory about the universe. In fact, he thought he could compute the total number of particles in the universe, which was the formula over there, 136 times 2 to the 56, because at that point, the fine structure coefficient was thought to be 1 over 136. Then the measurements increased, and he actually became more like 137. And then suddenly he realized, oh yeah, of course, I had to add 1. And then famously he was described as Sir Arthur add-on 1. But what's the modern point of view? Actually, here are the numbers. You see the number on top, which is the experimental value. It's less than, with an uncertainty less than 1 in a billion. And then there's the theoretical calculation below. I think it goes up to 10 loop diagrams, Feynman diagrams. So I think there are tens of thousands of these diagrams that you have to compute in order to calculate. So it's amazing. I think we should emphasize this. That if you want to find an area in physics that is really well known and experimentally verified to large precision, you have to go to the area of elementary particle physics. The precisions you find there, I would say only perhaps in mathematics where things are either 0 or 1. Nowhere else, I think, you find these kind of precisions. But what's the modern point of view? The modern point of view is an amazing thing. The fact is that the strength of the electric force is a function of the energy by which you measure it. So we have particles, give them a certain speed. For instance, if they're circulating around in these accelerators, an electron going around an accelerator, as it did, for instance, in the old lab experiment, had a larger charge than the ones, a E squared, smaller charge than the ones at room temperature. So, a crazy thing, the properties of matter change depending on which energy they have, or, by the way, another way to put this is if you think of high energy experiments as looking through a great microscope, it's the amount of magnification that you choose will change the properties of the force. And one way to think about it, that if you take an electron and you put it in space, there's this whole fluctuating sea of elementary particles, virtual particles, coming out of nowhere and disappearing again, that is changing the properties. And if you look closer and closer, this effect is stronger and stronger. And the electron is being shielded. That's not something that happens. So these properties change, and it's quite dramatic. For instance, if you do this for the strong nuclear force, it has the opposite behavior. If you go to higher and higher energies, the strength of the force becomes weaker and weaker and weaker. And this was one of the great achievements in theoretical physics that was honored with a Nobel Prize relatively recently. And so if you then look at the 3 forces in the standard particle, and you follow them up higher and higher energies, you see that their properties change and they're converging. It looks like they really want to be the same. And there's an area many, many orders of magnitude away from where we measure them at this moment experimentally, because this behavior goes with logarithmically in the size of the energy scale. You see they're almost passing through a single point. And one reason why we're enthusiastic about this, because it looks like that if you have a fundamental point of view at very high energy, that these might be perhaps 3 elements of one unique phenomena. And the plot becomes even better if you include another symmetry that I now want to mention, which is supersymmetry. So the question with unification always is it in our minds? Is it just, are we obsessed that we want to describe nature with one line? Are we obsessed that nature, we should have a single formula describing everything around us? Or is it something very deep in nature, that nature herself wants to describe in simple ways? So looking at these plots, we see this as a strong hint that there might be something going on at very high energies, which look deceptively like unification. Now, I mentioned supersymmetry, and supersymmetry, we saw some of the experimental consequences of supersymmetry in Maria's talk, but how do you think of it as a theoretical concept? I would say supersymmetry is the only symmetry that we haven't observed in nature, but we know it's consistent with all the other things we know about nature. So if you say, give me the laws of physics, can I improve upon them? Can I think of something that's not yet used, that's consistent with all the laws of relativity, of quantum mechanics, etc.? Supersymmetry is the only thing that we know. And in fact, there's a mathematical proof. It's the only thing that you can add to it. And it's a very strong, I wrote down here the algebra, the supersymmetry algebra, but it's relating 2 things, literally the 2 halves out of which we think nature is composed. So on the one hand, we have our forces and fields. Technically, these are particles with an integer spin, and we know the spin can be at most 2. So there are 3 cases, 0, 1, and 2. And nature uses all 3 of these options. Spin 0 is the Higgs field. Spin 1 are the usual force fields, and spin 2 is actually the gravitational field. I will say something in a moment. It's the graviton. And then you can have half-integer spins, and if something has half-integer spins, it behaves like a matter object. It's something, there's a fundamental principle that says if two objects have both half spin, it's the Pauli exclusion principle, they cannot be sit on top of each other. That's why you can sit on your chair, because basically your electrons and protons cannot sit on top of the electrons and protons, or cannot be at the same spot where the electrons and protons of your chair are. So that's why you, out of half-integer spin, you make something which is like matter, while of integer spin, they can be on top of each other, and that's why you can make a laser beam out of light, which is essentially a huge number of photons, which are all exactly the same, or exact clone of each other. In fact, it's describing spin and half particles, so describing all our matter particles, and the only theoretical option open in nature is to have a spin 3/2 particle, which would be like the super partner of the graviton, of the gravitational field, and would come with any supersymmetric extension of the world. So both in terms of fundamental principles and both in terms of the matter, there are two vacancies, which we are very much hoping nature will fill, because otherwise you will have a very strong, and we don't understand what kind of argument, not to make use of this principle. There's sometimes a saying, in nature or in quantum mechanics, anything allowed is obligatory. Nature basically pushes every button that you can push. It's like a small child, you're just pushing everything and using all that's out there. So in a more theoretical way, one way to think about supersymmetry is that there's another dimension in space-time. Now we think of space-time as described by coordinates x1, x2, x3, x4, like time. They are real numbers. They have a property we find absolutely obvious, which is just a number that 2 times 3 equals 3 times 2, which we say it's commutative. And in fact, in everyday life, we only use commutative numbers, so that's kind of obvious. But mathematically, you can also have non-commutative numbers. Nature used non-commutative numbers to describe our fermions. So if you want to, there is non-commutativity, which would be something like 2 times 3 would be minus 3 times 2. Would be kind of quite bizarre. But this can happen, and it seems nature likes this option. So you can think of, suppose we have an extra coordinate, which is a supercoordinate. It would be like pointing away from space and time, but in a very funny way, because if something is anticommutative, it basically squares to 0. So in terms, it's almost like an infinitesimal in the old fashion of Newton and Leibniz. With something that is, if you squares, it's 0. So you can take an absolutely minimal step in this other direction, but if you take a second one, it stops. So there's a very thin layer, in some sense, to nature. And that would be the way to describe it. So nature would have, in the same way as the realm of particles is nicely symmetric, having both bosons and fermions, commuting and anticommuting objects, space-time itself would have that property. But again, that's all speculation, because we have seen that if you would have a theory of supersymmetry, we have to find many, many particles. Every particle would have a mirror particle, and none of them have been found. But in some sense, what I now have told you are basically the whole arsenal of ideas we have. So this is our toolbox. We can have extra gauge groups, we can have unification of groups, we can have anti-commuting variables, we can have supersymmetry. So then we fasten our seatbelts and we go to gravity. And here I think it's a huge topic, and it's difficult to pay kind of justice, give justice to it in just 15 minutes. But of course we have seen in some sense, and you have seen that argument before. Now, we have two wonderful theories in nature. We have quantum mechanics, quantum field theory, particle physics describing the very small, general relativity, the theory of space and time describing the very large. And we feel there's only one nature, so they should come together. So how do these two things come together? Well, there are practical, experimental parts to that. We'll hear much more about that, I hope, this afternoon when cosmology will be center stage. But let's also just look at the conceptual level. So we need something which we call quantum gravity, which is kind of almost by definition anything that glues the two ends together. Now, Brian very elegantly explained to you what Einstein's theory of general relativity was, and I will just summarize to you, it's just a concept if you put anything in space-time reacts to it the curvature of space and time becomes a dynamical variable. It literally curves around in a very specific way described by very elegant formulas using the geometry of curved space. And then it's important to realize, by the way, that Einstein was extremely lucky that the formulas he needed and the whole formalism actually was developed 50 years earlier by a mathematician, particularly by the mathematician Bernard Riemann, who took him by himself, without any probing, the intellectual leap of thinking of higher dimensional spaces and thinking of space being curved, not being curved inside something else, but just curved by and through itself. So Einstein was extremely lucky. He had all the mathematics, basically he had his toolbox already filled. And he's in a very different position, I think, than we are right now, where math and physics are really working simultaneously at this, and with each other. And of course, as we saw, it's the movement as going as straight as possible in that curved space-time is the way we understand gravity. Now, you should realize that this really looks like a completely different picture than I told you what is the way we think about the other forces. Because the other forces we think about as an interchange of particles. It's basically this kind of tennis matches where you have two electrons and they hit the tennis ball being the photon left and right, and that's the way they are interacting. This is very different. These are ripples in space-time. And in fact, you can take the same, at least mental exercise. They say, well, think about these ripples in space-time and think of them, in particular, there are waves. And we have seen these waves indirectly in measurements. So not ripples in a field in space-time, but ripples in space-time itself. And you can think, well, dial down the amount of energy you put in. At some point, you will get little quanta, little bits of energy, and so you will have a particle. And in fact, you can compute what the properties of the particle are. It's again a massless particle, which means it can travel as far as it wants. It gives the 1/r² law. But to capture fully Einstein's relativity theory, it actually has to be a particle of spin 2, not of spin 1. So it's different from the photon. And in fact, we also know that there is room for a spin 2 particle in nature, but you can only have one. And so that should be gravity. So we know there. And if you're a particle physicist, let's do an experiment with two gravitons. It would be very difficult to do here on planet Earth. But you could think of having two gravitons scattering. And what are the properties? And you will find what is the strength by which gravity interacts with itself. And you find the number is actually Newton's constant. And a particle physicist would look at Newton's constant as 1/mass². In fact, in very natural units, the so-called Planck units, which Planck found actually in the year 1900, the same year when he discovered his Planck's constant, he knew that if you had Planck's constant, h bar, and the speed of light, c, and Newton's constant, g Newton, and you would have a kind of set of natural units. You would never have to use any units at all. No inches or meters or miles or kilometers, no confusing at all. There are natural units in nature. They are natural in the most literal sense of the word. And it would be a length scale, which is the Planck length, 10 to the minus 35 meters, which is roughly 10 to the 20 times smaller than the scales that are relevant for the standard model. And it would be similar an energy scale, which would be 10 to the 19 GeV. And just to remind you, the LHC is at roughly 10 to the third, so 1,000 GeV, or a TeV. So way beyond anything that we can measure. And there are various ways to think about this Planck length. I mean, one way to think about it is often said, this incredible effect of gravity that is so weak. And this is something that you probably not all realize at this moment, but it's something you can easily demonstrate. And so by comparing two forces, so if you compare the force among particles coming from, for instance, electromagnetism, or even more pronounced would be the strong force, if you compare that to the gravitational interaction between particles, the gravitational interaction is actually totally negligible, because in some sense, the one way to think about the gravitational force is that the charge for the gravitational force is the mass, and the mass should be done in Planck units, so that's actually incredibly small. And so if you were to think about how heavy particles should be, so that actually particle theorists, particle experimentalists would start to worry about gravity, then the elementary particles would roughly be the weight of a bacterium. And so there's this incredible factor of 10 to the 19th, that's the difference between the Planck mass and the usual masses that you have in particle physics. So another way we think about it is that, as I said, quantum mechanics give ripples in everything, in particular in fields. That's kind of this Casimir effect. So it should also ripple space-time itself. So there should be kind of a natural unit where space-time itself becomes kind of, we have used the word quantum foam for this, but it's just kind of a way of speaking, where space-time itself doesn't make sense. Another way to think about it, perhaps space-time is a little bit like this picture. If I zoom in and in, at some point you get the individual pixels. And there would be kind of atoms of space and time itself. And the size of the atom would be the Planck length. Incredibly small length scale. Now, so it's important to kind of see this in perspective. So here I just in one slide gave you both the largest size that we know, it is the size of our physical universe, and the smaller size. And quite conveniently, if you take the geometric mean, you find roughly the size of a biological cell. So that picture, the 60 order of magnitudes, that's in some sense one of the biggest questions we have in nature. It's the question, why is the universe so big? I think we'll address this afternoon. But there's another way to look at this picture, because people have endlessly speculated about the infinitesimal small and the infinite large. And they're kind of both out. Now, modern physics says, well, there's a largest scale that we want to understand. There's a smallest scale. They differ by a factor 10 to the 60, which is an amazingly large number. But it's a finite number. So at least we have phrased a good question. Explain to me where this number is coming from. And both the infinitesimally small and the infinite large do not really play a role in our physical theories, which is in some sense a relief. There are many, many philosophical and technical questions related to this. But if you're a particle physicist, there's another way to think about it. So we say, well, there are these self-interactions of the graviton that go with basically the equivalent of the strength of the force, which goes to 1 over the mass of the Planck. And there is an effect to this I won't explain here. But the fact that your interaction has the dimension of 1 over mass squared, it's both a serious problem and it suggests a solution. It's a serious problem, but the moment you start to compute these virtual particles, the things that can happen out of nowhere, if you have more and more of these particles, then actually the effect will be stronger and stronger. So I'm basically telling you that this fact makes your theory mathematically inconsistent. Now, it's not really a reason to give up, because we have at this point before in the history of physics. For instance, if you look at the theory of radioactive decay, the radioactive decay of particles, so for instance, you can have a proton decaying into a neutron. This is the physical effect. There was a wonderful theory for this by Fermi in the 1930s, and it had the same effect. It had a strength which was proportional to 1 over a mass squared, and that mass was 300 GeV, which actually is the mass, which is really the mass associated to the Standard Model. That theory, again, was inconsistent. But we have improved on this. In fact, the Standard Model has a different description of this and said radioactive decay is not just this kind of point interaction. In fact, it's the mediation of a particle that goes in between. In fact, it's one of these force-carrying particles. In this case, a force-carrying particle of the weak force. It's the SU2 part of our Standard Model. And in fact, that's a particle with a mass. And the fact that its mass is around that order tells you why the effect goes like with 1 over the mass squared, because that's just an explanation. So the previous picture, this picture was kind of a caricature. You have to zoom in, and then you see actually this kind of this intermediate thing going there. And that explains it, and then the whole thing becomes well-behaved. And you have this wonderful tool that you can compute many, many, many orders of perturbation theory, and it does make sense. So you can argue perhaps there should be something similar in graviton-graviton scattering. There's like an intermediate W boson, the equivalent for that, which is something which have typically a mass scale which comes with the Planck mass. And so roughly that's one way to motivate any theory of quantum gravity, particularly something like string theory, by saying, well, there are lots of other particles. The particles, you don't see them because they're very heavy, but actually they smooth out the inconsistencies and make the theory well behaved. Well, string theory, which is the idea that particles, even most fundamental particles, are not really zero-dimensional points, infinitesimally small points, but are little extended objects that can vibrate, has many, many consequences. So it's, of course, a good topic to have a 10-hour lecture course on. But the best, simple thing to know, if you look at a string, it can oscillate, it can vibrate, just as any other string does. Actually, according to the same mathematics as the mathematics you learn of a simple violin string. And the lowest order of vibration actually produces a spin 2 particle. So you can think of a string as a dressed up graviton. It's a graviton together with many other particles that make the things behave well. And in fact, if your string moving through space-time, it not give these spaghetti strands, not these one-dimensional world lines, the thing we call the world sheet, a two-dimensional surface. And you can look at the interactions of these strings, and just at the pictorial level, you see that this picture looks much more smooth than the pictures that you draw in particle physics, where any particle physics process, you have two particles hitting head-on. So these are infinitesimal point-like objects hitting head-on and producing a third particle. Here we have these kind of floppy strings moving and gluing together, making these beautiful two-dimensional surfaces. And the smoothness of these diagrams, particularly if you have loop diagrams, translates into a mathematically consistent theory. So the great thing is of string theory about all the other issues it has. It produces for you a mathematically consistent way to describe gravity, to describe quantum gravity, to describe quantum gravitons. And that's already a terrific thing, because that's at this point also the only way we have managed to do so. Now, there are many consequences of string theory. I just want to mention one and then stop. And the one thing is actually we talked about extra dimensions. So just going through the list, Einstein added time as an extra dimension. And then we thought that supersymmetry might add these kind of funny infinitesimal anti-commuting dimensions. But what about a real physical dimension? And this actually something was explored very early after Einstein's discovery of relativity theory. In fact, it's called Kaluza-Klein theory because it happened in the 1920s. And a great story, because the paper was actually given to Einstein to referee. And I think he sat on it for 3 years, not reacting, and just because he was so triggered by the idea. And I think, I like this. This was his idea of unification. And one of the effects is if you have a particle that can move in the fifth dimension, in particular if the fifth dimension is a little circle that can go around, there's a lovely mathematics. If you think of a particle going around in a circle, under the laws of quantum mechanics, it cannot go at any speed. It's kind of its speed is quantized. Basically, it can go once or twice or 3 times. And if you see what that means in the rest of the universe, in the uncompactified 3+1 dimensions, it turns out that you're describing a particle with an electric charge. A charge that's 1, 2, or 3 times the elementary unit of electric charge, which would be the single quantum going around the circle. And if you see what happens, so there's this very simple formula that if you take gravity in 5 dimensions, 5 space-time dimensions, and reduce it down to 4 dimensions, you get gravity together with electromagnetism, kind of for free. And you understand why charge is quantized, you get the nice properties. It all works lovely. In fact, looks wonderful. There's only one big but, which is, and I can all of you challenge to do the calculation. It's a very simple calculation. Basically, we've done it already. Just compute what is the size of this extra dimension. Given the fact that you want to describe electromagnetism, you want to describe the charge of the electron. We know the charge of the electron, so you can just compute what the size of the extra dimension is. And there you find kind of a difficulty, because you find that the size of the extra dimension is of the order of the Planck length. So that means this idea, this great idea of extra dimensions, can only work if you're comfortable enough to talk about quantum gravity. Now, Einstein, of course, was really fighting tooth and nail many of the consequences of quantum mechanics, only making it stronger and stronger. Now, every attack he had, there was a wonderful answer, and it became even better. But it's a very poetic thought that his ideas of unifying the forces through geometry and extra dimensions only do make sense if you embrace the ideas of quantum mechanics. And in fact, in string theory, and Brian is really the person to talk about this, being an expert in this himself, because we have a much more convoluted situation where we not have one extra space-time dimension, but depending on particular physical model, up to 6 or 7 extra dimensions that can each of them be curved in a very complicated way. But they do unify particle physics, I would say in the spirit of Einstein, in the sense that the shape of the internal dimension, I already described that just if you add an extra circle, the length of the circle will translate into the charge of the electron and the properties of electromagnetism. But in the same way, if you introduce more of these extra dimensions, you can what we call geometrical engineer physics in the remaining 3+1 space-time dimensions. So particle physicists become kind of higher dimensional sculptures. They have to think of these spaces in order to reproduce the thing that was on the t-shirt on the right-hand side, which was the laws of physics. Now, of course, there's again a big why question, which is why that particular space dimension? And as I promised, any why question, I would move ahead to the next speaker. I think we'll see this consistently throughout the day. Because on the one hand, it's beautiful. I mean, this is my final slide. I think Einstein's fundamental idea of unification is saying, well, I took this bizarre phenomena of gravity and explained it almost away by using the geometry of space and time. That idea actually is still valid and alive. And I think in string theory and many other theories of unification, actually that's what we do. We think actually in terms of using geometrical tools and geometrical language to capture some of these questions. But I think actually even Einstein would argue that, yes, indeed, he has a beautiful theory. He liked general relativity very much. But it's a theory that allows for many, many solutions. So this question, why that particular space? Why is it curved like that? I think that still has to rest. And I think that actually is, I think, a perfect point to end this talk. Thank you very much.